Thanks. Let's begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. I thank you for the rain and for the pleasant weather outside. Just pray to be with us today. Help us to glorify you, Lord, what we do. I pray that you'd prepare these students' minds and hearts for the test tomorrow, that they could do their best, Lord, for your glory. In your name I pray, Lord Jesus. Amen. All right, so make sure your homework's up here. No, okay. So, ignoring, of course, the hypersphere problem, is there anything that you guys found particularly vexing? All of it? Gosh. 85? All right. Well, if it's all of it, I guess I'll go problem by problem. Surely everyone got minus 1/20th for problem 77? Show of hands.
Wait, I don't remember. What was the question?
Don't remember. How many got number 77? All right, very good. How about 78? Some? Okay. How about 79? All right. The hands are waning. Yeah. Yeah, buddy. I will not accept the answer, yeah, buddy. Do you guys understand the reason we have to change the order of integration on certain problems? Right? Because sometimes you can't do the iterated integral over x first, or you can't do the iterated integral over y first. So if you change the bounds, it may be that when you change bounds, you can do the integration with respect to the other variable, and so it's an important technique to be aware of, to change from type 1 to type 2, or to type 2 to type 1. How do you actually do this? What's the critical thing you need to be able to understand? The relation between the bounds on the integral, right, and the region which you're integrating over. So make sure that you have a clear understanding of the interplay between the numbers which are on the top and bottom of the integral signs, as well as the graph to which they represent, right? So in other words, be able to graph simple things in the plane, like in Calculus 1 and Calculus 2. Any questions about this one? Okay. This one was unfortunate because I think I said in the first octant the other day in class, it's not in the first octant, right? It's below the xy plane, which means, I don't know. It's not in the first octant anyway. I'm not sure which octant that is in, but anyway, it's not the first octant, right? Where the volume is, it's below the xy plane, which means what I'm doing here is backwards, right? These really should be flipped the other way around. So to make up for that, I put minus the volume of B is what I'm calculating, right? As one of you pointed out, I do the thing. At the end of it, I get a negative number. I know what I did was I had it set up backwards, right? So I just go back and say, aha, I calculated minus the volume, not the volume. And so I took your advice, and I did that, so as you can see. Anyway, I get 1/72. Yeah? Okay, I see some nodding. Some hiccuping. Let r be bounded by x squared plus y squared equal to 1, x squared plus y squared equal to 4, y equals x, y equals 3x. So basically, you just got a sector. I don't think you guys have questions about this, no? Most important thing here is when we change to the polar coordinates, right? Remember, dA in polars is r d theta. But in this case, I do r d theta dr because I wrote the theta bounds first. It wasn't really, you could flip the order of these, it wouldn't matter as long as I also did that. Everybody get 83? So 83, we're looking at a volume which is bounded by the cylinder, r equals to 1, or x squared plus y squared equals to 1, and these planes, z equals 1 and z equals 2 plus x plus y. Thankfully, they're not intersecting, right? I guess they might intersect at a point. If y equals 0 and x is equal to minus 1, I guess we also get z is equal to 1. Yeah, these do actually intersect at 2 points, but they're on the edge of things. So there's always a clearly defined top and bottom, although they do meet on the edge in one place here. Anyway, once you've convinced yourself what the top z and the bottom z is, then we just do an integration with respect to polar coordinates, right? I mean, cylindrical coordinates. Everybody understand what we're doing here? Yep. Go ahead.
Can you always just say if you have a cosine or a sine of an angle and you're integrating over the whole?
Well, as long as it's not like cosine squared or cosine to the fourth, I mean, we got to be careful, right? It has to be like a naked cosine.
It's even something that you can't just, it's not just a completely acceptable function either.
That's right, but the integrals add, right? So I can, this is the sum of 3 integrals, and those 2 integrals have a multiplicative, there's a cosine multiplicatively in those summands. I mean,
Still trying to figure out when you can and can't do that.
fair enough, but I mean, that you can do. That's not an overarching answer of what you can and can't do, but this you can do. Anyway, did you guys get pi? Okay. I mean, if in doubt, work it out. Oh, sorry. Sorry, for some reason that reminded me of Jesse Jackson's Democrat Party convention speech many years ago. He told America that they needed to get out of the bushes, and they started shouting, "Get out the bushes! Get out the bushes!" I just thought it's the most awesome speech. I really liked it. It's still relevant today. But anyway, use spherical coordinates. Oh, I'm sorry, you're all Jeb supporters. How dare I? But because we're all so excited about Jeb. But oh, I'm sorry. Is there a presidential election? I don't know. Whatever. So this is rho, the spherical radius, right? And if b is a solid ball, that means we should use spherical coordinates to calculate this integral, right? So the critical thing here, you must have in mind, if you're going to do an integral over spherical coordinates, we must make account of the Jacobian factor, which is this rho squared sine phi d rho d theta d phi, right? So the rho squared and the sine phi are coming from dv and the change of variables theorem, all right? So if nothing else, you must have clear in your mind, what do I do when I'm changing the polar coordinates to cylindrical coordinates and to spherical coordinates? It wouldn't be too surprising to me if 40% of your test was on these things, right? Coordinate change is a very big part of my test. It's most of the interesting problems because it allows for problems that look difficult but are actually easy, right? Which is kind of my go-to thing on tests, right? Well, I think they're easy. You can disagree, but it's your prerogative. It's a free country. Any questions about this one? Why am I integrating from 0 to r, from 0 to 2 pi, and 0 to pi there?
You don't know what the radius is.
Oh, I was given that the b is a solid sphere of radius r in the problem statement. Back up here. Let b be a ball of radius r centered at the origin. Calculate that triple integral. Or a solid sphere, you could also call it. So in spherical coordinates, the inequality is just r is larger than or equal to rho. So that means I integrate from 0 to r in the row coordinate, and that gets the whole sphere. And then theta and phi, well, where are they in that picture? Well, they're free to range over their natural domains, right, which is 0 to pi and 0 to 2 pi. I forget which one I said first, but sorry. Either be right or wrong, depending on whether you're a mathematician or a physicist or an engineer. Physicists and engineers typically use theta and phi in the opposite sense of mathematicians. It's very annoying, but it's the reality that we face. You can tell which coordinate system they're using. If they change to spherical coordinates and they put a sine theta here, that means the meaning of their theta is opposite the meaning of our theta. And like the roles of phi and theta are interchanged. If you see somebody put a sine theta when they do this step, that means they've interchanged the roles of theta and phi as we've been discussing them. You're like, why would anyone do that? I don't know, but it's been done for like a couple hundred years at this point, so I guess we just have to deal. So this one I chose to not be, I chose the easier way to think of it, I think, which is the outside, right? So the rightmost region looks like that. It's still unpleasant, right? So I have to integrate from 4 cosine theta at the top down to 2 in the inner radius. And the points of intersection are plus or minus pi over 3. So to calculate the area, I have to do this integral, right? And that gives me this 1/2 16 cosine squared minus 4, which when you do the half angle identity, it gives me 8 times 1 plus cosine 2 theta. None of this can be ignored, right? Everything here contributes. It's unfortunately over from minus pi over 3 to pi over 3, not from like something nice like 0 to pi or 0 to 2 pi. And I get 4 pi over 3 plus 2 root 3 for the area. By symmetry, the y is clearly 0, right? So the centroid, the center of, the centroid's x-coordinate times the area should be the integral of, see, I recommend doing something like this when you're doing this calculation, right? Because the thought of dividing by the area in 1, 2, 3, 4, like 5 expressions seems rather unfun. So why not just multiply by the thing you don't want to keep writing at the start, and just remember you're not calculating the coordinate for the centroid, you're calculating area times the coordinate, and then you can at the end divide by that and get what you want, right? So I'm giving you advice on how to be lazy. So the integral of x dA, though, again I face these lovely fascinating bounds, and I have this time to integrate x dA, which gives me r squared cosine theta dr d theta, and that gives me that. And then you integrate and you get this. Now I showed you how to do the cosine of the fourth integral the other day. I don't really feel like doing it again, so I'm just going to leave it at that. This is an insignificant dot. This is not supposed to be an I. Do not, this looks like it might be an I, but that's just some kind of, I can't get it off, I'm sorry. It won't come off. Anyway, so I get about 2.642 once I run the numbers. And that makes sense to me if you go back and look at the original graph. That looks kind of like ballparkish. If you look at this, right? The inner circle is radius 2, right? So 2.6 is, it's kind of just, it makes sense that would be where the centroid is for this region. It looks right to me. Any questions or comments? Concerns, conundrums?
Oh, never mind. Okay, you took the 2 out. I was wondering how you got a 4 inside there.
Ah.
Okay, I'll let you know.
Now, if I was to take the other interpretation, I decided to use Luke's solution because I'm lazy, and because I didn't really feel like doing the integration, which broke into 3 pieces because that seemed awful. Anyway, we can see what the answer should have been. If you did that right, you should have gotten 1, 0 as the centroid of that region. Now, if you ask me what the centroid was of the other sort of the moon-looking thing over here, I don't know. Yeah, I think you're right. I think it would be, I feel like it would be minus 0.6 0, 2 or whatever, kind of like 0.6 beyond the edge. We had like 0.6 beyond the edge for that one, so it should be like 0.6 beyond the edge for that one since there's a symmetry here. But anyway, on the test, I will try to be much less vague about which is the bounded area. I would invite you to take the viewpoint as in the future, if you're given a problem in your homework which is ambiguous, right, what should you do? You should ask, right? Now, if you're not a nice person, you should just pick the easiest possible interpretation of the problem and solve that one, because I can't really take off your points. And then tell me about it like right before it's due, then I can't really change the problem, right? Why am I telling you this? Oh my gosh, no. You should tell me as soon as possible so I can clarify it for you, right? Anyway, problem 86. I get 8 pi alpha over 3 times 5 plus c times r to the 5 plus c power. Yay. That wasn't sarcasm, right? Ah, dang it. Was that sarcasm? I lost track.
I didn't have the 3 on the bottom.
Yeah.
Otherwise, that's what I got.
No 3? Where'd my 3 come from? It's the integral of the sine cubed is the 4/3.
It looks familiar, but I'm like not entirely sure.
How many people got the r to the 5 plus c power, at least in their answer? All right, well, that's good. At least that's something, right? How many people don't know how to integrate sine cubed? Yeah, good. I like the hesitance because that is definitely something I might ask you. I hope you know how to do that. How many people can integrate d theta? Okay, all right. Sorry, let me not be.
That should definitely be on the test.
It definitely have lots of integrals of theta on the test.
That could be its own problem.
Definitely worth like half the points.
I bet I can make the integral of d theta look complicated.
No, just put it like that.
Just like that? Oh, okay. I'm just kidding. Here's the integral of sine cubed if you forgot. This is an important kind of problem. It's very likely I have a problem like this on the exam, right? Because it's nice in the sense that it really tests whether or not you understand what the integration means, the coordinate change. There's a lot of nice features to this problem, and it also has that really nice thing. It looks difficult, but it's actually simple. So you look at the bounds, what you have is x is between -3 and 3, and y is between this square root function and that square root function, right? But if you explore the equality here by squaring either side, you get 9 minus x squared equals to y squared. But hey, that's just x squared plus y squared equals to 9, right? In other words, what you have is a disk rather, of radius 3. And so in polar coordinates, these are the bounds, right? In some sense, it's a polar rectangle, right? It's just rectangular bounds in the polar coordinates, 0 to 2 pi, 0 to 3. And then I look at the integrand, which is 12 minus r squared minus r. Can you see that? You should see that. You should be looking for x squared plus y squared, or minus x squared minus y squared as being r squared, right? Look for that. Because I may not be so kind as to give you a problem that says use polar coordinates to substitute. Maybe I just want you to know that. I want you to internalize this idea that when I'm faced with certain problems, I should be thinking about polar coordinates, I should be thinking about cylindrical coordinates, I should be thinking about spherical coordinates. I might take the training wheels off certain problems and not tell you that's what you have to do, right? I might leave them on. I haven't decided yet. Kind of depends on the problem, but it's being written. It's in flux. So anyway, with that said, is there questions about what we're doing here? Do you guys get it? Yeah. There's no restriction on theta. It goes all the way around. So theta goes from 0 all the way to 2 pi. Yeah, the earlier problem we looked at, the one with the... Well, this one, for example, theta was stuck between minus pi over 3 and pi over 3. This one back up here is a little bit simpler. Here you see we had an extra condition on the region we were integrating. We were stuck between these two lines, so theta was restricted, right? If there's no restriction on theta, it goes all the way around. Unless there's some other statement, like say y was greater than 0, or x was greater than 0, or maybe x and y are both less than 0. That would put theta between pi and 3 pi over 2 or something like that. If you had x greater than 0, what would you take for theta? Here's x greater than 0. Now, some people would say, well, it's 3 pi over 2 less than theta less than 2 pi, and 0 less than theta less than pi over 2. I say this is not the right way to think when you're thinking about integration. You almost certainly want to take these and geometrically just go, well, I'm going to do this. Right? Like that's what I would do, because that way I can do one integral rather than an integral from 0 to pi over 2 and then 3 pi over 2 to 2 pi. That's a drag to do two integrals when I can just do one. So you kind of got to be smart about the way you use theta. Be geometric. Abuse the 2 pi degeneracy of the angle. Right? You can identify pi over 2 with 5 pi over. You can always add 2 pi, right, to suit your purposes. And you're ideally you want to do an integration over one interval of theta rather than 2, if you can get away with it, right? Just a thought. Anyway, yeah.
The only thing that could have limited theta in that problem was the x and the outside of the
Let me go back to that problem. Where was it? Which one were we talking about? This one?
The x is just negative 3, which is just the bound of the circle already. So if it was any different from that, it might have limited it.
Oh, yeah. Yes, certainly if I had something like, I totally agree with that. If I had the y bounds as they are, but I say I had minus 2 less than or equal to x less than or equal to 2, well that would certainly be a drag, because then instead of having this, you'd have this. And this region is not nearly as pleasant to integrate over as the whole disk. Totally agree with that. I'd have to really think about how to break up theta in that case. It might be inevitable. Depending on what I was integrating, I might have to break it into two pieces. Yes, sir?
I think there was a problem with using this question.
Sure.
If we didn't realize that, like, first angle was pi over 4, that it was between 0 and pi over 2, how would, like, we be able to calculate that?
So the question really is geometrically, how do you change from a line y equals x to polar coordinates, right? So there are different ways. Personally, I just look at it and go, well, that's pi over 4, because I recognize that as being whatever. But more generally speaking, this will be the tangent of the angle times x, because the slope is y over x. So for a non-vertical line, this is an identity, which is true. So this I can read that tangent of theta naught, is equal to 1, and that tells me that theta naught is equal to pi over 4, because I can take the inverse tangent of 1 and get pi over 4. Another way would be just take y equals x and convert to polar coordinates. So it's like r sine theta is equal to r cosine theta. And again, we get to tangent theta is equal to 1. There's lots of different ways to get at it. Generically speaking, when you're trying to figure out an angle or something, take whatever it is you're given and then try to convert to the new coordinates. Use geometry if you can get away with it.
So we shouldn't use, like, the inverse tan of y over x for that? Like, you could
Well, you can use inverse tangent of y over x. It's just dangerous. Okay, so that's inverse tangent of what? 1 in this case, right? Which is, pi over 4. Great. But how about this? Y is equal to minus x, right? And then you say, oh, okay, well, theta is inverse tangent of y over x. And then you'd be wrong, because you get inverse tangent of minus 1. calculator would spit out minus pi over 4 because the calculator puts you down here. So you can use inverse tangent, but you got to use it with understanding that it's only going to give you angles in quadrants 1 and 4, and it's going to lie to you if you're in the other two quadrants. So you have to adjust. But anyway, this is hopefully not a new story I'm telling you, but it's a story that students get tripped up on. Yes?
Do you have to do any sort of proof, or can you just say that, oh, I know that y equals x is pi over 4 just because it's halfway between 0 and pi over 2?
Yeah, I think I don't require proof that y equals x translates to pi over 4. No, I don't expect
in the
this.
test, if we're converting, if we don't need to, if we just look at it, we can see that, oh, this is that angle. Can we just use it?
You can just use it, yeah. Just beware that if you're wrong, then it's hard for me to give you partial credit. That's just a generic comment, though. All right. We were to problem 87? Yeah. Problem 88. My current test has something like this on there. I forget exactly, but basically the idea is here, if you make a linear change of coordinates, you have to think about how each line segment transforms. But as I told you, a nice result that you can use, I give it to you for free, is that if you're transforming something like really any kind of closed polygon under a linear transformation, if you just transform the vertices, then if you connect the dots of the transform region, you'll get the new region. So all I really have to do is look at the corners 0, 0, 2, 4, 2, 5, 0, 1, and see where those go. And that will tell me what the new thing is. And it's the same story as usual. When we do a substitution for an integration, there are two things we have to do, right? We have to change the bounds, and we have to change the measure. Changing the measure is done with the Jacobian, which works out to 2 in this case. Now, so here it is. If you calculate partial u v xy, that's kind of easy because of the formulas you're given here, right? Like, you can easily see that u is equal to x over 2 and v is equal to y minus 2x. So it's really natural to calculate this Jacobian. But when I'm changing from xy to uv, I actually need the opposite one, right? So you can use the reciprocal rule to get from this one to that one if you want. Alternatively, of course, you can solve those equations for x and y and just take partial derivatives in u and v directly. It's up to you. Anyway, whatever floats your boat, the point is we get a factor of 2 here when we calculate the Jacobian. And then, of course, this is the 4u. And then you just integrate, right? Now, here I used a trick because I noticed that it's the same in u and v. So I can rewrite this as like 2 times 2, which is 4. And then I just got integral the square root function from 0 to 1. I've got 2 of those, so just square it and do it once and answer. That's just a trick. That's not an essential point. Yeah. We also saw that trick in the integrate the Bell function to find the integral from minus infinity to infinity e to the minus x squared. We use the same trick to rewrite that integral there. But anyway, not an essential point. Not. Any questions about this one? I know there's a lot of details, but do you see the game plan? You given a problem like this? Yeah. Yes, sir.
How much partial credit would we get if we calculated Jacobian and got the curve in the equation?
Oh, for the homework, I would assume a significant partial credit, yeah.
Well, then we use the wedge product instead.
You use a wedge product instead? If you got the right answer, I'm happy. Actually, I'll just be happy if they're graded at some point. 89. It's kind of neat how this simplifies down, right? So cos squared minus sin squared is 1. So I end up with u squared cos phi for the volume, for the Jacobian. Do you guys get that? Yay! All right. You guys should go study with them. No. If you're, no, 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 it's a bad idea.
That's what I got. So many hours doing that.
Yes, in fact, it is pi squared r squared over 2 is the hypervolume. Yeah. Not. I have not recently worked this out. I'm tired, you guys. I'm sorry, but it does work out to rho cubed sine squared alpha sine phi. So. Anyway, so that's pretty much it for the homework solution here. Yes, sir.
This one you gave us an R is equal to 1.
Oh, r was equal to 1? Oh, okay, so it should be pi squared over 2 then. Yeah. Oh, it's because it's a unit 3 sphere. I think it would be wise to look at this one. Ah. So I think these end of chapter problems are good to look at if you haven't already, in terms of, kind of sort of test questions you might think of. I don't know. Sorry, I need to take a break from serious business for a minute. Hey, stop that. So the question is, an armored government agent decides to investigate a disproportionate use of electricity in a gated estate, foolishly entering without a warrant. He finds himself at the mercy of Ron Swanson at 100, Dwight Schrute at -110, and Kakashi in a tree at 113. Supposing Ron Swanson inflicts damage at a rate of 5 units inversely proportional to the square of his distance from the agent, Dwight inflicts a constant rate of damage of rate 3 in a sphere of radius 2. If Kakashi inflicts a damage at rate 5 units directly proportional to the square of his distance from his location, because if you flee, it only gets worse the further as you run as it attacks you as you're retreating, then where should you assume a defensive position as you call for backup? What location minimizes your damage rate? Assume the ground is level and you have no jetpack and or anti-gravity devices. So what I have to do is I have to come up with a formula, right? So first of all, forget about Schrute. Like, it's kind of like a discrete thing, right? He's either inflicting damage on you or he's not. So just like set him aside and just consider Kakashi and the other guy. What was his name? Oh yeah, Ron Swanson. You consider Swanson and Kakashi. Swanson's got the 1 and Kakashi's 2, and then I just got to minimize that function basically. So I look for critical points, and I find. What do I find? Do I find no critical points? I guess I find no critical points. But then I have to think about the Schrute sphere, right? Which is distance. That's on the edge of the Schrute sphere, Schrute starts inflicting damage upon you. And so if you analyze the Schrute sphere, you find that, what did I found 2 points. Oh, I did? It's been a while since I worked this problem. What did I figure out?
On the right there, white.
Where was it? I'm sorry.
At the bottom.
Which ones are these? These are on the Schrute sphere?
No, that's,
These
you
are,
account for whether x
Oh.
is equal to 1 or not.
so that's x is not equal to 1. Those are the,
And then there's no solution, but if it is equal to 1.
if x equal to 1, oh, so then I have y equals to, oh. I get y over y to the 4th, huh? Equals y minus 1. Oh, that gives me this crazy equation, which then gives these solutions. I see. So those are actually critical points for the damage function. So I have to check those points, and then I have to check the Schrute sphere and see where my damage is.
You actually got 3 points.
3 points, yeah. Yeah, right. 0, minus
So maybe
0.82.
you're like right in your own space.
Yeah, right. So I think what I decided was either A or B will work, so which you choose depends on where your agent starts. Ah, I see. But anyway, this is kind of obviously a difficult problem, right? But there will be some problem on your test which is like a simpler version of this kind of thing, right? Which is what? I mean, this is a really crazy way of asking a what? A closed set test, right? So how do you if I ask you to do something like, so when you think about optimization, what are the 3 major things you have to worry about? One, of course, is the classification of critical points as paired with the study of what? Multivariate power series, right? That's the one thing to worry about. The other thing to worry about, of course, is just basically Lagrange multiplier type problems, right? So there you're given some constraint and you're asked to maximize some objective function on that constraint curve or surface. Then the third thing, right, are closed set test problems. Closed set extrema problems. So a typical one of these is something like, here's some closed set, I don't know, it looks like this. You've got some function f of xy, and then find the absolute extrema of f of xy on this closed set. So what do you have to do? How do you actually do this? It's a 2-pronged attack, right? You find the critical numbers, find critical points rather, in the interior, right? And then what else do you do? That's one. And then step 2 is you analyze f restricted to the boundary of D, right? How do you analyze f restricted to the boundary? Well, you either use Lagrange multipliers or you just straight up parameterize the function on the boundary, right? We looked at problems like this, like find the maximum value of a function on a triangle or a square, remember? We had to check, are there points inside where you've got critical points, right? And then if those don't, and then how do you figure out which is the winner and which is the loser, what's the max and min? Well, this gives you a finite list of points, right? So you just list them and pick the one that gives you the largest output or the smallest output, and there's your max and min. Now, so obviously this I don't see this test having 14 problems. I see this test with like 8 or 9 problems probably, right? Because I'm going to ask something like that, and it's going to take you 20 minutes to work it out at least, right? And I'll probably ask some integrations which actually take you a little bit of time to work through. So make sure you're rested. Right? You will need your wits about you tomorrow. Right, let me put this away. Are there questions specifically about, say, like the last mission? Or this one, or anything? Yes, sir.
It's not really a question about the mission, but I was wondering, since we just got the mission answers for this mission today, could we move the test to Wednesday and go over what we're going over Wednesday? That way we get more than just 24 hours to study the last mission.
Tell you what, I'll make the test next Tuesday. Oh, what's the catch? The catch is I will be covering new material the rest of the week, of course, yeah. See, this is the weirdest thing. It's like if I built into the syllabus, right? If in the syllabus I announced at the start of class, all right, guys, I'm going to cover all the new material up till like Friday of this week. And then next week, I'm going to cover new material, but then the test is going to be on the week after that. It won't cover the new material, right? But it's going to cover all the old material. Typically, students complain. And yet, in the semester, when you do it on the fly, everybody's like, yeah! It's the weirdest thing.
Just figured out how to get your students to love you. Just practice it.
Yeah, of course, I had not planned to do this. This is all Barrett's idea. I give Mr. Lyon his due. No, I mean, it's next Tuesday. The test is next Tuesday. And then, of course, there is the inevitable, like, two people this rains on the parade of. And all the studying. But, this doesn't go away. Like, okay, I shouldn't say. This stuff, the optimization doesn't play too much of a bigger role in the larger story of this course. It's kind of an isolated event, right? Like, unless I was to come up with some really dastardly problem that somehow rolled the whole course into one thing and also somehow involved optimization. I haven't thought of that problem yet. Oh, I should think about that problem. But no, okay, so ignoring me being malevolent, this is hard to work into the later material. The multivariate integration, it's the bread and butter of like most of the interesting things we do past this next test eventually come back to multivariate integration again. So it's really important to get that down good so that you're not battling that when we talk about Stokes' theorem and divergence theorem and such. So anyway, the other good thing is with this particular material, there's almost no way you could get confused about what you're studying right now by looking at the next material. Sometimes that's an issue with tests, right? Not with this one. So anyway, next Tuesday then. Tomorrow, line integrals. Yes. Thank you guys.